All right, guys, so I'm going to walk you through a skill that I think is like just criminally underemphasized in probably like every physics class, and that is how to turn equations into a proportionality. Because proportionalities are like the foundation for doing so many other things and answering so many other types of questions correctly. And once you see this very simple method for doing this, you'll be like, oh, that was so easy, but it felt so hard or complicated or confusing at first. So, if you haven't heard of a proportionality before, I'm going to tell you what it is and what it does. So, when we look at equations, they are equalities, right? Like what is on the left is equal to what's on the right. And they give us a way to explain the relationship between quantities. Proportionalities do that too, but in a little bit of a different way. So rather than saying the left is equal to the right, it says the left is proportional to the right. So if we make changes to what's on the right, the same change is going to happen to what is on the left, but they're not equal to each other. It's more, I like to think of it more as keeping a balance. So let's walk through an example first with a more simple equation, just so you get a feel for how to do this, what a proportionality is if you don't know. And then we'll do this again. Our second example will be with an equation that's just a little bit more like complex. So that you can see how this works for something that's like a little bit different looking. The other connection that we'll make here is not only how do we create the proportionality, but how do we use it? How do we use it if we have a question like if we double this quantity, what happens to that one? Or if we want to turn that into a graph, how do we make a connection between proportionalities and graphs? Because that is also a super important application of proportionality. So let's go ahead and get into it. And we'll start here with Newton's second law. So Newton's second law tells us that acceleration is equal to net force over mass. And I'm writing it in this way and not as net force equals mass times acceleration because this is written in like this cause and effect setup. So it's like the acceleration depends on the net force and the mass. It's not like net force does not depend on mass and acceleration in real life, if that makes sense. It's like depending on what net force and mass are, like that's what your acceleration will be. So anyway, we're going to explore here how acceleration relates to net force, and then separately how acceleration relates to mass. So when we look at this equation here, to literally just turn this equation into a proportionality statement, there's two things that we are going to do here. Number one is that we need to take out the equal sign, right? It's like we're not writing an equation, we're writing a proportionality. So to do that, what the proportionality symbol looks like is this. All right, so we're gonna like drop out that equal sign, we're gonna put the proportionality symbol in there. And the next thing that we're gonna do is we're going to treat anything in there that's not the variable that you're trying to see how it affects the other thing, we're gonna replace it with a 1. So if we're trying to figure out what is the relationship between net force and acceleration, we're gonna put a 1 in there for mass. So we can just say, and of course, like net force over 1, we're not going to write the 1 actually in there. So we see here that acceleration is just directly proportional to net force. So if we have a question that's like, okay, well, if we double the net force, how does that change our acceleration? Here's where we start to think about this idea of balance. So by doubling the net force, you're doubling the right side of the equation, right? Or the proportionality. So if I double the right side, and not just net force, but it's like we're looking at the whole side. We're doubling the right side. The left side will double as well. So it's like whatever factor the right-hand side changes by, the left-hand side will change by that factor as well. So let us also make a little connection here to a graph. So generally speaking, when we look at this proportionality, we're going to treat the left-hand side as our dependent variable. So that goes on the y-axis in your graph. And on the right-hand side, that's going to be related to the x-axis. So if we just have one thing on the right and one thing on the left, and we graph acceleration and net force, that's going to give you a linear graph because you just have a direct proportionality. There's a linear relationship between acceleration and net force. If you double net force, acceleration doubles. This is a really simple one. So let's do one that's a little bit less simple. We'll look at the acceleration and mass relationship. So again, if we turn our equation into a proportionality, we're going to treat net force as a 1, and we see that acceleration is inversely proportional to mass. So on a very general level, that tells us that if the mass goes up, the acceleration will go down. Inverse relationship. So in this case, if we double the mass, overall doubling the mass decreases the right side of our equation by a factor of 2. Doubling the mass cuts the right side of our proportionality in half because that 2 is in the denominator. So if overall our right-hand side gets cut in half, our left-hand side gets cut in half as well. So doubling the mass will decrease the acceleration by a factor of 2. On a graph, there's 2 things that we can do with this. If we're trying to graph acceleration and mass, this is going to look like a graph of y equals 1 over x. Okay, so if we take mass to be what's on our x-axis, we're graphing y equals 1 over x. That graph looks kind of like this. If we want a linearized graph, we are going to straight up take whatever is on the right-hand side, like the whole thing, and put that on our x-axis, and that is going to give us our linearized graph to tell us that acceleration is proportional to 1 over mass. All right, so again, we're turning the equation into the proportionality. We're just dropping out the equal sign, replacing it with proportionality symbol. Anything that's not involved or it's a constant, we're replacing it with 1, and then we have our proportionality. That proportionality can tell us how changing one factor is going to affect the other, and it gives us a way to get a correct graph shape, just to summarize. So let's take a look at an equation that is a little bit more complicated. Okay, so this is one that I like to give for okay, here's an equation that's probably one of the more complex ones that you're going to see for doing this in a course like AP Physics 1, Honors Physics, CP Physics, and that is the equation that tells us the period of a mass spring system. So a mass spring system, the period is how long it takes to complete one full oscillation. M is the mass, so that's T is the period. M is the mass, K is the spring constant. And the spring constant is how easily you can stretch your spring. The higher the spring constant is, the harder your spring is to stretch. So not that matters because we're just writing the proportionality. But if we are trying to see, well, what's the relationship between the period and the spring constant? And then if we double the spring constant, how will that affect the period? Let's walk through that, and then we'll also we'll look at the period and mass, and we'll make a graph. So if we are trying to isolate the relationship between the period and the spring constant, we're going to take the 2 pi, that is a constant, we're going to treat it like it's 1. The mass is a constant, we're going to replace that with a 1. So we can write the right-hand side of our equation like this, Or we could also write it like this. Either one of those, same thing. So if I were to double the spring constant, overall, that's changing the right-hand side of our proportionality by a factor of 1 over the square root of 2. Notice by doubling k, that 2 goes on like the inside of the square root, with like right with k. So if I change the right-hand side by the factor of 1 over square root of 2, the left-hand side changes by that factor as well. See how this is like very simple? Like once you know what side or what the right-hand side changes by, you do the same thing to the left. Like no matter what it is, no matter how complicated it looks, it's like whatever happens to the right happens to the left. So that means that this side will also change by a factor of 1 over root 2. Let's take this a step further. Let's say that you have this question where the period for the mass spring system is like the original is 5 seconds. And now we've replaced the spring with that has a spring constant of double the previous spring constant. If we double the spring constant, what will the new period be? We're literally going to take the old original period that we had with the original spring, and we're going to multiply it by a factor of 1 over square root of 2, whatever that comes out to be. And that's the period with the new spring and spring constant. All right? Simple, right? So again, if we were to like draw the linearized graph, we would be putting t on the y-axis. And if we want it linearized, we're going to literally put like 1 over square root k on the x-axis. That gives us the linearized graph. All right, guys, we'll do one more quick one with this same equation. So what if we're talking about like the relationship between the period and the mass? So if you feel like you kind of have this idea down, just pause the video here for a second. Try this one on your own. See if you can write the proportionality for the period and m, the mass. And what would a linearized graph, like what would be on your axes for a linearized graph of this relationship? Okay, pause it, try it. Or if you're not sure yet, just keep listening and I'm gonna walk you through it. All right, so if we're looking at t proportional, or the proportionality between mass and time, t is proportional to the square root of m. So if we are trying to linearize a graph here, if we put t and square root of m, we're going to get that linearized graph. If we're just looking at, okay, well, what would be the graph shape if you have t and m? That is going to look like a graph of y equals square root x. So your graph shape is going to look like kind of like this. All right? So how'd you do? Let me know in the comments. Did you get it right? Did you mess up? Like what did it look like if you messed up? Because maybe it'll help out some other people as well. And if you realize something that you were doing wrong, but then you like kind of corrected it in your mind, let me know, because it really, really helps other people to see, oh, well, I thought this at first. This is my like incorrect thinking, but now I realize like this is what I did wrong. That's so, so helpful. So if you did that, just write it in the comments. Nobody's going to judge you because everybody does this wrong at least one time. Probably you're going to do it 25 times, but hopefully not because you watched this video. So I'm going to give you one last, we're not going to walk through this example. I'm going to give you this as a question. And this one, I want you to put your answer in the comments. And then I'm going to come back. I'm going to let you know if you got the right answer. But let's see here. So here's my challenge to you, if you have made it this far in this video, is we're going to use Newton's law of universal gravitation. So if you're familiar with what that looks like, gravitational force is equal to constant G, m1, m2 over r squared. So this is like if you have two masses that are a certain distance r apart, what is the gravitational force between them? Like I said, big G is a constant. So I want you to do a couple of things here. Number one, write the proportionality to show the relationship between gravitational force and the distance r. So just write the proportionality. Number two, if the distance r between these two objects decreases by a factor of 2. So if we cut it in half, what is the new gravitational force, or what happens to the gravitational force? And what would you have to graph to get a linearized graph? So graph the linearized graph for the relationship between FG and R. All right, try it out. Put your answer in the comments. Let me know how you felt about it. Like, did it feel easy to do this after this video? Let me know if this helped you. And if you're looking for more content like this, like if this video helped you out, you need some more like instructional stuff like this, put it in the comments. Let me know what you are struggling with so I can make more videos to help you guys out, because I know physics is tough. There's a lot of skills that I think are underemphasized, and then you're kind of left like figuring things out on your own, and that can be really hard. So let me know what you need from me, and I will make more videos based on your guys' suggestions, and I'll see you next time.